Lesson 9.2 is about tangents to circles. Okay, we'll start the lesson with a simple theorem, and that theorem can be proved, and it is in our textbook, and that's that a line that's tangent to a circle, so it intersects the circle at one point, and that point is called the point of tangency, that if I draw a line from the center of the circle to the point of tangency, so I draw a radius to the circle, that tangent line is always perpendicular to the radius. So I form a 90-degree angle with the radius of the circle and the tangent line. So because the tangent line is always perpendicular to the radius of the circle, the converse is also true. I know that if I have a line that's perpendicular to the radius of a circle, it must be the tangent line, or a tangent line. So a corollary to the previous theorem is that if I take a point outside a circle, as I have right here, and I draw from that point tangent lines to the circle, so these intersect the circles in single points of tangency, these two tangent lines, or tangent segments, are congruent to each other. Okay, so tangents to a circle from a point outside the circle are congruent. Now, it's a real interesting little proof of that, and it goes something like this. If we take the radius lines to the points of tangency, we know that every radius line is the same length, distance as every other radius line, so those two little segments are congruent. We also know that if I connect from the point straight through here, that this line is common to both triangles that I've created, and so that's congruent to itself. So I have two kind of back-to-back triangles, and I also know that these are right angles created with between the radius and the points of tangency. So by hypotenuse leg to hypotenuse leg, I have two congruent triangles. Therefore, these third sides as corresponding parts must be congruent, and so that's a little proof of that. Okay, next we're going to talk about common tangents, and these are tangent lines that are touching two circles at a time. So if I have a common tangent, it's tangent to two or more circles at once. And first is a common internal tangent. And a common internal tangent is a tangent which, if I take the centers of two circles, any two circles, and I connect them with a segment, the common internal tangent crosses that segment. Okay, so it crosses like that midline that's drawn between the two centers. So if it crosses it, then it's called a common internal tangent, and we'll contrast that in a minute with a common external tangent. Okay, a common external tangent is a line or segment that's tangent to two or more circles at once, but it doesn't cross over that midpoint, that segment that connects the centers of the two circles. So if this line doesn't cross the blue dashed line, then I call this a common external tangent. So you're going to want to get pictures of that kind of in your mind. Okay, this is a picture of two what we call internally tangent circles, where one circle is inside of another, and there's still one point of tangency, and they converge at that one point, so we could attach a tangent segment to it. But the circles are what we call internally tangent. So here's the center of one circle and maybe the center of the other, but they do have a common point of tangency. Now I'm going to have you get that in your mind, and then you can contrast that with two externally tangent circles coming up. Now, two externally tangent circles look like this, and like internally tangent circles, they share one point of tangency, one point that they intersect at, that they have in common. But as you can see, one circle is not inside the other. It's not internal to the other circle, so we call these externally tangent circles. So just to recap, at the top of the page here, these are internally tangent circles sharing one point of tangency, one circle inside the other. And at the bottom of the page here, these are externally tangent circles, still sharing one point of tangency, one common intersection, but both circles are external to each other. Okay, lastly we have diagrams here where we have circles that are inside of some polygons. And to be inside the polygon, the circle is tangent to the sides of the polygon, to each of the sides. So it doesn't overlap, it just exactly touches and intersects with the side. So the sides of the polygon become, each of them, tangent segments to the circle. And when we have this, we say that the circle is inscribed in the polygon. So again, the thing that's in the inside is the thing that is inscribed. And so I just use the in to mean inside. So in these diagrams, the circle is inscribed in the polygon. If I'm talking about the polygon with respect to the polygon goes around the circle. So I say the polygon is circumscribed. Again, it goes around it, so I use the cir to remember that. Polygon is circumscribed about the circle. Okay, so that concludes the vocabulary and concepts related to tangents of circles.